Hi everyone, welcome to our first week after having had the chance to contemplate the fundamental theorem of calculus. I hope you continue to appreciate it, or your appreciation continues to grow. Today we're going to work on using the fundamental theorem of calculus to evaluate definite integrals. And in order to do that, we need a bunch of different rules, just like we have for our derivative rules. So let's just remember our fundamental theorem, which says that if I'm trying to find the area under little f, as long as I can think of an antiderivative, meaning a function whose derivative is little f, all I have to do is plug two numbers into that antiderivative and subtract. And as long as you can think of the antiderivative, correctly plug in the two numbers, and correctly subtract, you'll get the correct area under the curve. You don't have to worry about rectangles or limits or anything like that. So some properties of these definite integrals that we'll be able to use. These first two, I think probably you might use without even realizing that they were properties. If you have trying to find the area under the sum of two functions, that's just the two separate areas. So you can break it up just like we can with derivatives. This really comes from our same derivative rule. So we won't bother to try to write a formal proof of this. It comes from our sum rule for derivatives. Because the derivative of a sum is the sum of the derivatives, the rule works the same backwards. Similarly, we had this constant multiple rule for derivatives, right? This k takes the graph and it stretches the graph vertically by a factor of k. We learned that the first week. So what should that do to the graph of f? So suppose k were 3. You had some area under f. Suppose f had 5 units of area under it. Now you multiply by 3. Everything gets stretched by a factor of 3. So how much area should the new graph have? I hope you're all saying 15, because when I stretch by a factor of 3, all the y values became twice as big. All your rectangles become twice as tall. So we get 3 times what we had before. In other words, if you already know the area under the function f of x, so you know the area under, say, x squared, and you want to find the area under 3x squared, you can just multiply by a 3 out front. So we'll often talk about pulling this constant k out front of the integral. And that's what this particular property allows us to do. Sometimes we will run into a case where we have these limits in the opposite order of how we want them. We usually want the bigger number on top and the smaller one on the bottom. But if we see something the other way around, we can still handle this. So this is our definition of the integral. This is the limit of the right-hand Riemann sum, except that now it's the other way around. We usually have a b minus a here, but now because of this, we have an a minus b. But we can fix this. If we want to switch the thing on the inside to be how we normally like it, in other words, I really wish that I had a b minus a here, what have you really done? You've really multiplied on the inside here by what number? What did you multiply a minus b by to turn it into b minus a? You multiplied it by a -1, right? But if you multiply by a -1 somewhere in the problem, somewhere on an expression, then you've got to multiply by another -1 somewhere else, so that altogether you've only multiplied by 1, which doesn't change anything. And we can multiply by that -1 out front if we like, because this -1 is a constant. And as we talked about when we were doing our constant multiple rule for derivatives, you can pull constants in and out of limits as much as you like, because whether I multiply by a -1 on the inside or the outside makes no difference. Whether I multiply by a 3 on the inside or the outside makes no difference. So if you find yourself in a situation where you wish these were reversed, you can always just put a negative out front and then go from a to b in the usual way. So that's the third of our 3 useful properties. And this has a practical explanation as well. So for example, if you imagine that, again, this is f of x is some rate of change. And if you know that when you integrate the rate of change from, say, time 3 to time 8, you add, say, 1,000 people to the population. So it's like you're watching a movie and you watch it, the movie starting at time 3, going to time 8, the population goes up by 1,000. What if you now reverse the order and you watch the movie backwards from time 8 to time 3? Then you would see the population go down by 1,000. So if this were a positive 1,000, when you reverse the order, it becomes a negative 1,000. Maybe the population wasn't the greatest example. Maybe it should have been something like water coming in and out of a tank, where when you watch the movie forward, the water level goes up. If you run the film backwards, the water level will go down. And that's what happens. Running it one direction gives you a positive. Running it the other direction is the negative of what you got in the first direction. So last week, the other thing that we said we need to come up with is a list of a bunch of different antiderivative rules. We came up, remember, we spent 2 weeks coming up with all of our derivative rules. And if we had never come across the connection, the fundamental theorem of calculus, the connection between areas and slopes, then we wouldn't be calling these antiderivatives, we'd just be calling them integrals. And we would have to come up with all of these integral rules, again, from scratch, by hand. It's possible to do that, but it's a lot of work, and we don't need to do it because we have this fundamental theorem of calculus, which says that finding the area is the inverse process of finding the slope. So this list of basic antiderivatives, which are also called indefinite integrals, remember, these were definite integrals because they had actual limits here. So when you evaluated a definite integral, all of the ones that we evaluated last week, we got a number as the answer. This, an indefinite integral, there's nothing for me to plug in. So what this is saying is saying, give me all the functions over here whose derivatives are x to the m. So we want to think about using our derivative rule backwards. So if we ended up with x to the m, what must we have started with before we took the derivative? So you can think back to last week when we did x squared. If we wanted a function whose derivative was x squared, over here we wrote what? X cubed. We added 1 to the exponent, and then we divided by the new exponent. And we also said that we can always add a constant to that, and that will just shift the graph up or down and therefore not change the slope, not change the derivative. So this is our power rule for antiderivatives, for integrals. Except we have to be a little bit careful. What is the one value of m that we cannot plug in here? What value of m will make us divide by 0, which is not allowed? That's m equals -1. So this works as long as m is not -1. So that means there must be a special rule when m is -1. What's another way of writing, from the very first week, what's another way of writing x to the -1? How could I write that as a fraction? We could write that as 1 over x dx. Remember, this dx is just part of good grammar for us at this point. We're not, this whole thing is one expression. We can't break it up into the different parts. It's like the dy dx looks like a fraction, but is really the actual derivative. So do you know a function whose derivative is 1 over x? I hope the function that comes to mind is natural log of x plus c. But there's one complication with this. What is the domain of natural log of x? If you think back to week 2, the domain of our natural log functions is only positive x values. So I can only put positive x values into this. However, can I put negative x values into this function, 1 over x? Definitely. So we have to change this a little bit to allow for us to plug in negative x values over here. So that's what I've got trying to show with this graph here. This is the function 1 over x. And just as a specific example, I'm looking at 2 to 5 and -5 to -2. Because of the symmetry of this graph, the area between 2 and 5 and the area between -5 and -2 should be the same except opposite of each other, opposite in sign. So we think that the area from -5 to -2 under this graph should be the negative of this area. We know a way to compute this area because we just find the antiderivative ln of 1 over x, which is ln of x. The problem is with this one. So let's see if we can find a solution to that. If I try to do just the normal thing here, write ln of x, and evaluate that from -5 to -2, we run into trouble because we're plugging a negative value into ln, which isn't allowed. So I hope that at home you're guessing a way to solve this problem. And I hope that your guess involves putting absolute values in. So if we put absolute values in here, now let's see what happens. So now I can plug in ln of absolute value of -2 minus ln of absolute value of -5. And that is legal to do because the absolute value of -2 is 2. So this is just ln of 2, and this is just ln of 5. So that's perfectly OK. Now let's just check if it does equal what we want. Let's see if it equals this. So this is the same as if I put a negative out front. Right? If I just factor out a -1 from this, I get this. And this is what I would get if I did the integral from 2 to 5 of 1 over x dx. Right? Because if I integrate 1 over x over a positive interval, I don't have to put any absolute values in. The integral of 1 over x is ln of x. I plug in the 5 and the 2 and subtract. So what we've shown is that the integral from minus 5 to minus 2 is the negative of the integral from 2 to 5, which from our picture is what we want to make happen. So this is a long way of explaining why we need, whenever we're writing the antiderivative of 1 over x as an indefinite integral, meaning we don't know that we're plugging positives in here, we have to put absolute value signs there to take account of the possibility that this is eventually going to be used for negative x's. All right, that's by far the longest of these. Now let's do the rest here. E to the x. Do you know a function whose derivative is e to the x? It's our favorite function almost, isn't it? E to the x plus c. Do you know a function whose derivative is b to the x? So like 2 to the x or 3 to the x or 10 to the x. Well, by our exponential rule, we know this must have started with a b to the x. But if I take the derivative of b to the x, I get b to the x times what? B to the x times ln of b. We don't want to have an ln of b over here. So we need to do something similar to what we did up there to fix the situation. And that is to divide by ln of b. Because now, if I take the derivative of b to the x, what do we get? B to the x times ln of b cancels the ln of b on the bottom, and we just get b to the x like we're supposed to. And of course, this e to the x is a special case of this one. So if you don't want to memorize the e to the x one, you can just remember this one. How about sine of x? Do you know a function whose derivative is sine? I think we talked about this last week, negative cosine. Do you know a function whose derivative is cosine? Sine. Now you might think that I skipped a trig function here, right? Probably you're thinking, what about tangent? Well, do we know a function whose derivative is tangent? If you think back, did you ever take some function and then take its derivative and get tangent as the answer? And I think you'll say the answer to that question is no. We know the derivative of tangent, meaning that if I wanted, I could have written what over here? I could have written secant squared of x, and the integral of secant squared of x is tangent of x. But we don't actually know a function whose derivative is tangent. But we should put the secant squared, so let me put that one over here on the side. So the integral of secant squared x dx is tangent of x plus c. But we don't know what to write if we have the integral of tangent. There is such a function, and you'll figure it out when you take calculus 2. It's the natural log of the absolute value of secant of x. You can check that on your own if you want. Do we know a function whose derivative is this? We sure do. That's arcsine. And do we know a function whose derivative is this? We sure do. That's arctangent of x. And we could write one for a negative here, but the negative is already taken care of by our rule here. So if you see negative 1 over the square root of 1 minus x squared, you could say that that's arc cosine of x, and that's perfectly correct. Or you could use this rule and pull the negative out front, and then you would get the negative of arc sine of x. And so you should contemplate that for a second as well, that the antiderivative of negative 1 over root 1 minus x squared is both arc cosine of x plus c and negative arc sine of x plus c. So that will tell you something about how the graph of arc cosine and negative arc sine are related to each other if they have the same derivative. So we got all this lists in just a very short amount of time here, unlike the 2 weeks that we spent coming up with the derivative rules. And again, the reason that we were able to get all these so quickly is because of the fundamental theorem of calculus. We know that finding areas is deeply related to finding slopes. We already know how to find slopes. Therefore, we get all of these formulas for finding areas essentially for free. And we'll stop this video segment now, and then in the next one, we will practice using these rules to find some antiderivatives.